Okay, we're back. Part 2. Got our workout in. Break. Yep. Alright, for those of you who didn't watch part 1, we are learning about recommender systems and at the building our own. We've built sort of a neural collaborative filtering tool. We want to expand it by making tests, learn about the concepts, use the based collab, item based, and so forth. Then hopefully in the future make a series recommender system. Thanks, Jimmy. To have you back as well. What are you guys up to today, by the way? I'll move the mic so it doesn't sound too much. long tail property. That the feedback is in way through the YouTube setting of back. The readings are currently different and we can see positive problem ratings among satisfied real world to property. According to this property, only a small item rated frequently. We have some pop. That's called the long tail property. Seen that term. The voice is cutting. I tried to fix audio a bit. Remove them. I don't know if it's better now. I was trying to add a noise suppression on it to see if it was better, but maybe it wasn't. I don't know. Let me know if I just activate this, if it's better or worse, because then I can keep this but remove the noise gate maybe. Okay, cool. All right, I'll keep it like this then. Yeah, so I was saying that we have, let's see, we were going through this long tail property. I guess this has implications. Such a rating distribution has important implication for the recommendation process. In many cases, the high frequency items tend to be relatively competitive items with little profit. I wonder why that is an implication. I guess it doesn't necessarily have to be the case, but might be a general trend that the items that are bought frequently are competitively priced or something. But I feel like this leads to a conflict in the general sort of recommender systems. It's not that recommender systems are bad inherently, it's just that the incentive for companies are to make more profit. Or for example, YouTube has a recommendation algorithm that wants you to watch as much as possible, right? That might not be your objective function. You might want to watch that has the most amount of impact or gives you a sense of, you know, fulfillment after watching something, that maybe you want to just learn something. Because if I watch like YouTube Shorts or TikTok or something, I feel worse after having watched that, even though it's fun and really addicting sort of when you're watching it. And I feel like this is also, if this is the case, right, that Amazon, for example, makes profit from the lower frequency items because they have higher profit margins, right? Their objective function is not to recommend you the items that you want that will actually make the most impact on your life, they want to recommend you what they will make the most profit on. Yeah, the name of the book is Recommender Systems, the textbook. I think it's it seemed to be the highest cited book on recommender systems. It's a bit old though, it's from 2016, so it's not maybe the most updated, but it will give us the basics and relevant concepts, and then we can read papers for state of the art. From my time reading this book, can you describe collaborative filtering? Yeah, I think I can. Collaborative filtering is where you have, first of all, you have a matrix like this, where you might, let's say we're looking at movies. So as the columns, you have all of your movies that you have in your data set or in your library. And the rows would be all the different users that watch the movies. So one row here represents the user 1 has rated movie 1, or I don't know, this is The Godfather, he's rated it 5 out of 5. This is Interstellar, this is 5 out of 5. And then some other movie, Toy Story, got 4. And so this is the his ratings, and then there are similarly for all the other ones. Now we want to learn a actual, well, you can do different. So collaborative filtering has a different way. It has memory based or model based. But if we're looking at a model based, like we did implemented, which is neural collaborative filtering, which is quite simple. I'll show you. So for neural collaborative filtering, we do something like this, where we get the user ID, movie ID, and a rating. So user 1 has rated movie 1, The Godfather, and he gave it a rating of 5. So that's all we have. And then we have a neural network in this case that tries to learn an embedding for both the user and the movie. So the embedding here hopefully learns something like, this user is very interested in thriller movies, or this person really likes comedy. And then you have an embedding for each movie, which hopefully is an embedding maybe that learns that, yeah, this is a comedy movie, for example. It obviously learns more complex things as well. But in this case, the neural network just does an embedding of that. It concatenates the user, what the user likes, and what the movie is. And then it runs it through a linear layer and predicts a single rating for that movie. So this is model-based because it is a learning sort of a sort of a space for each user and the movie. So collaborative filtering takes the entire, let's see if we can do this more compact maybe. The collaborative filtering takes this matrix of ratings for users and movies and tries to create a space, a representation for each user and movie at some feature space. So that's what the embedding is doing here. If you instead look at content based, it is starting off from this embedding. So we have created features, and then it just tries to learn the prediction, if that makes sense. By embedding between uses between them, what the network learning patterns. I'm not sure I understand your question. Like here, the embedding is learning a representation for each user and the movie, because we don't know the movie, what sort of genres it is, or maybe more complex things as well. Like, yeah, I don't know. You can imagine all sorts of stuff here that it tries to learn. It's a black box, right? We don't know what it's learning. And then it simply concatenates what the user likes and what the movie is about. Hopefully it learns that, and then it can find out, well, is this fitting? Yeah, so I've done something similar like that before with cosine similarity. I think if you do cosine similarity directly on the ratings, that is memory based, if I'm not mistaken. So this would be model based. If you, however, do something directly on the matrix itself, rather than learn an embedding space or learn some type of representation, then it's memory based. But it's still collaborative filtering. It's just two subsets, memory based and model based. That's what I've learned so far. Do you mean embeddings are more likely finding most similar users than giving me based on my favorite movies? Let's see. So wait, I think the prediction problem is a little bit different, because you can do, like here, he's talking about that there are two primary types of neighborhood-based algorithm. You have user-based collaborative filtering and item-based. I'm a little bit confused about this. I don't know if I can explain this part, but like you can use these, I think, in two different ways. Like you could find an embedding space. So you could find an embedding space for a particular user. You could see, all right, for each user, which is closest in the embedding space. So you can take like these 5 users are closest to you, meaning they probably like the same stuff. Then you can take what do these guys like that you are close to or similar taste in movies, and then you can take the average rating of those 5 people and give the top ones to you because you probably like the same thing. Now that would be a user-based collaborative filtering. What you could also do is, let's see, so you could also do item-based, where you could take the items that you like. So you could take, all right, we know that you like The Godfather and Interstellar and the Martian. So if you like those 2 movies, which are closest to those 2? And we could look at the movie embeddings that are closest to those movies. And then we could recommend those to you. And that would be item-based. So when you say, do you mean embeddings are more likely finding most similar users than giving me based on my favorite movies? Then I'm thinking that leads to the prediction problem, which you could do in different ways. And I guess both of those has pros and cons. Will this code be uploaded to your GitHub? Yeah, I think now I'm just learning. Similarly, if someone watched the Lightning series, now I'm just learning about this. So this will probably not be uploaded, but later on I'll make a series, hopefully, on a recommender system, sort of sharing what I've learned, and so people can learn about it and follow along that don't want to watch the stream. All right, let's go back now. So this is a big problem, I guess, that we have popular items because the distribution of these items leads to the one at the long tail are very few in numbers. So then it might cause evaluation problems, right? We can't just look at, we need to use some type of something that takes into consider imbalanced classes, but that's in chapter 7. All right, so here's an example of the long tail. So there are a few items here that are very popular and have a lot of ratings, and other ones that don't have it. Okay, so here we go. Here maybe is a more detailed, perhaps, on what was asked. Predicting ratings with neighborhood-based methods. The basic idea is to use either user-user similarity or item-item similarity to make recommendations from a ratings matrix. No, I don't think this book has practical coding stuff. We will try to do that ourselves. This is just theory, concept based, but we'll try to convert these ideas in practice. So yeah, we talked about this. We have user-based models, item-based models, and that's pretty similar to the explanation I gave, I think. Similar users have similar ratings on the same item. Or we have item-based, similar items are rated in a similar way. You can probably use ChatGPT. Yeah, we can probably do that. If we get stuck, we can probably ask it for help. Can you tell me which software? This is Drawboard. I don't know if it's that. I don't know if I love. It's pretty nice. I know a lot of people use OneNote as well, but yeah, I haven't found the perfect PDF reader so far. User-based neighborhood models. So here, one idea that I think here is important is this, where one user might be biased towards liking most, whereas another might be biased towards not liking. So we have optimists and pessimists, and we need to consider that by normalizing ratings. One measure that captures the similarity between the rating vectors of two users is the Pearson correlation coefficient. So here we are sort of normalizing the predictions, the mean rating, and then we're using Pearson correlation coefficient, which is this thing. You should check out Turi Creates Rex's implementation. Do that. Do you have a link? Oh, is that like a... I have not done a video on reinforcement learning, but it would be cool to get into that in the future. I have studied it a bit, but I've not made any videos on it. So right now I would like to add like a split for the code that we have. So here I would like to split it. Like this. So that we have our training set and test set, and then we can, I guess we don't have to do test, we can do val. We'll just do a test and val. Or let's keep it as, yeah, let's just do this. Do you think it would be better to build a deep learning workstation or use cloud GPUs? I think a combination, depending on what you want to do. So I think for experimentation, you definitely want to have something local, but sometimes you're going to build something really large and you might have to rent 8 or a couple of A100s or something, and for that I definitely think it's a lot cheaper to just rent it when you need it. So I'd say both. Build like a simple small workstation where you can do a lot of experimentation, and then rent when you need something large. Wonder what's wrong here. So we're getting index get. You pass in a validate a little, but no validation step. All right, we should add that. I mean, that should be here, I think. I don't like to do self like this. I don't know. I just like to write forward, so it makes more sense. I think we're still gonna get the error, but yeah. Key error 1. Well, that seems right. So we do get the number of movies and the number of users. Not sure what could be going wrong then, because let's see. Self-df ratings.locate. So I have 800K, right, for the training. Where's the error going on exactly? Maybe it's easier if we do, we just do num workers equals to 0. So 0, we are getting index error. How is that possible? Oh, maybe because of the header, maybe? It doesn't seem like it. I can only imagine it has to do with this thing, because that's the, like, I can only imagine it has to do with this. Yeah, we could try ChatGPT. I mean, this is probably like a dumb thing. just want to get the first, like the row of it. Yeah, so here you get name, all of that stuff. So that will be, can you also get this? I always forget, like, what's the difference between iLock and just okay, so if we do this and then that works. Okay, so what if we do here instead of doing it multiple times? Maybe that would also be more efficient. So we take row, okay, cool, we got it. Okay, nice. Hopefully this works then. Let's keep it, and then we will do, I mean, I think this is unnecessary probably anyway, so we can do user ID, no, user ID, movie ID, rating, and I don't know why it does this, row, oh, that's why. Okay, yay. Okay, we'll fix that error as well. Where is it? Torch.set flow 32 matmul precision medium. I wonder if this was slower or faster. I guess we're not limited, probably. I don't know. I feel like it should be faster anyways. But we need to have some metric. Let's see. Thing is, I don't really know what metrics are used. I know RMSE is used. We can probably ask Copilot. Use RMSE from Torch metrics. Yay. And then we can compute it in the, oh no, this is not where we should have it. Let's move it down here. And in the training step, that's not what I want. There we go. And let's copy the same thing if it works. Maybe we should skip to the chapter 7 in the book and see what... Oh, see, this is the problem with Copilot. You just trust it and then it does something completely insane. So what do we have? RM. Cosine similarity. That's nice. We'd probably want to implement that. I mean, it's nice to know exactly how it works, but cosine similarity, mean absolute error. We can use that probably, but I would like to use root mean squared error lightning. PyTorch. There we go. Mean squared error. So they don't have... okay, well, let us use the just the mean squared error then. I mean, that's the loss. So metrics used in recommender systems. Predictive accuracy metrics. It is best suited for ratings, mean absolute error, mean squared error, root mean squared error, and normalized mean absolute are the most important measures. We can probably use that. I mean, it's gonna be the same, I think, because that's what we're using anyways. All right, whatever. We even have fallout and hit rate and precision, so I feel like this should be okay. We can use those later on, but let's use mean squared error now. Functional. Oh, it's not sklearn. We didn't add it to the validation step. But I guess it's going to be the same. But yeah, welcome to the stream, Vladimir. Good morning. We are coding some, just continuing from the neural collaborative filter. Wait. I'm tired. Yeah, neural collaborative filtering that we coded last time. But now we're trying to, so we converted to Lightning code, good. Now we are trying to split it, and we are trying to add an evaluation metric. And so we're trying to learn how to do all of that. And we want to see that it is actually learning something, which it does seem to do, but I don't know why. So we're getting the loss here, but I've added, I feel like there's something wrong because we are gonna need here train loss and then train MSE. I don't know why it's doing. Why it's not doing, it's adding loss, but it should be adding val loss and train loss. Is it because I'm returning it? But I feel like, oh, I think I know what's wrong. So let's see, we need to, when we are logging it, we need to add it to the progress bar. On step, on epoch true, progress bar true. And then let's also do it here. There we go. And now we should hopefully get train and val loss. Let us read your code meanwhile. Package install. Yeah, let me know. I can walk you through what we've done so far. Cosine similarity is used. No, it is used. I think cosine. I'm still trying to figure it out, but cosine similarity seems to be when getting. Let's see, when actually doing the predictions. I think comparing when you using sort of user embeddings or item collaborative filtering, I think. I don't think it's used for the actual evaluation. I think it's used for the prediction. Evaluation seems to be this hit rate or sort of precision or mean squared error or something. Okay, so train MSE 1.2. Val loss step, val MSE, huh? MSE step. It's too long. We need to add TensorBoard or something, but maybe we can do just, we can remove the on step thing. So the question is, how do we actually like use for evaluation now? So we made a split. What's the like state of the art like metric? What do we use? Or like what's the most common metric? Is it hit rate or something else? I mean, we have the book, so I guess we can go to that. And maybe it would be easier because this is such a movie lens recommender system, Python. So this is the question, like how do you do the actual prediction? I mean, I guess here you could just send in the user and the how would you solve the cold start problem? I mean, this is a cold start problem is a general one, right? We're assuming now we have some ratings, and so we build from that assumption. But if we don't, I guess I'm not sure what are used most commonly, but I guess the most popular item or the like. Yeah, just the most popular one for a particular user, for a new user maybe, or the highest rated ones in general. He goes into it later in the book, and we haven't gotten there yet. Link to stream. Can you quickly show what data we're using? Yeah, we're using the movie lens. We have three. We just have this. We have a user ID. That user has rated a couple of movies, and he's giving a rating for each. We're using the 1 million part. I think there's one that's larger as well, but this is just to get us familiar. All right, so here we have train loss and val loss, and they're pretty much the same. So I guess we haven't overfit yet. I mean, this should be like a movie lens Kaggle here. And movie lens, like competition 2 years ago, 8 years ago. Not that many teams, but if we just go to data sets then. All right. But so wait, so if we just do, I mean, for a particular user, we could just run the neural network, right? Trainer has no attribute to evaluate. Wait, what? Oh, validate. Let's say you make the users rate some movies in the beginning. Now you have some info about the user. So how would you recommend to that user? Yeah, so this is what we're trying to figure out, right? This is where we are right now. We want to learn how to make the actual predictions. And in the book here, he goes into like you have user-based, I think it's like user-based collaborative filtering. Maybe we can do this, Ken. Let's go to ChatGPT, okay? Let's try if he can help us. Welcome to the team, Vladimir. Thanks for becoming a channel member. Let's see. So ChatGPT. Let's go. Is anyone paying for the ChatGPT, by the way? Like the $20 or whatever? Oh no! You see this? Sometimes you can still access it. Like if I use another browser, I have it cached or something. Hopefully. Come on, come on, come on. We need you. We need you, ChatGPT. I am human, I think. See? See, we're in. All right. See, like you can get this sometimes, and then you can try it on something you have cached, and then you can still manage to get it. So, okay. So wait. What is the question? The question is more difficult than the answer. We're trying to figure out how to What's the difference between what's the difference between how about we use KNN to find the nearest user embedding? Let's see. So user-based collaborative are two different approaches, right? In user-based, recommendations are made based on the similarity between users. And I think this is where we use cosine similarity or whatever. The system looks for user who has similar preferences and recommends items that they have liked. I don't know. This is completely wrong, right? Like I'm thinking, okay, so this is my idea. I guess we can do that here when we're doing the prediction, right? We could send it, we could get the embedding for a particular user. I mean, okay, so let's see. The easiest way I'm thinking how we can do prediction now is we can send in a user and every movie ID, we get all the predictions, we rank them, and then we get, all right, these are the top 5 movies for which the user has not already rated. That would be a simple way, right? And I don't see why that would be an issue, actually. But the other way is that you could send in and get an embedding for that user. You could look which users are closest, get the average rating of those users, the movies that they've rated, take the sort of a weighted average, or just, I mean, an average, and then you would take the highest one out of those. Now, I don't know why that would be different, but you can only do that for the users present in the data set, right? But that would be, we can't do it. We need to have users in the data set. We can only do it for users that we know about. If we don't know anything about the user, then I mean, every recommender system will be bad initially. I think there's just no way of solving that problem. So here we have, let's see. Yeah, validation loss, val, MSC. I mean, they're exactly the same. But yeah, I don't know. I mean, this doesn't make sense to me. I think ChatGPT is just making things up here, probably. I don't trust this answer because maybe it's completely right, but it seems like, yeah, I don't know. So does Netflix retrain its Rexus each time a new user comes? I don't know how. I guess, I mean, if you have a new user, you would probably just recommend trending movies or like popular movies right now or something like that, or top rated movies. And then as they watch more movies, you get more info on the movies that they like, and then you can actually, you know what I mean? And then you can actually and then you would retrain your model so that it gets a good representation of those users as you've collected more data. So Netflix definitely does retrain their system as they collect more data. Hello, Carlos. And yeah, ChatGPT is not perfect. I don't trust it completely. Okay, so how they evaluated it is by having, okay, they take the item that the user interacted with the last. Okay, so the last prediction, it takes it out, it leaves it as a test set, and then it computes. We follow the common strategy that randomly samples 100 items that are not interacted by the user. So we predict. Okay, so we do prediction on. I'm not sure how this is done, but I guess you could just run the neural network and get the ratings, and then you rank the test item among the 100 items, and then you have hit ratio. And I guess, I mean, the closer it is to the first one, or actually I'm not sure how you would do that, because you don't know if the other ones are better, maybe. Okay, but the hit rate intuitively measured whether it is present. Yeah, so we have if it is. It may be a different topic. No, link sharing should not be turned off. I don't think so. I can change it. I don't know how to do it though, but it should not be. Can we infer initial preferences for new users from other in a different area? I think for sure we can do that. Like, it depends. This is application specific on how you would do that. But yeah, so I do think that's quite possible to do. It just depends on the application, and it might be different for and some are easier than others. If you do online shops from the news they click on, that might be difficult, but you might have history on some type of user that has sort of told you what kind of age and gender and location they live in, and then from that you could maybe build some very, very simple that predicts based on where they live and so on. Or you could also, maybe you have their occupation and so on. Maybe that gives you what they might be interested in. Someone that works in IT might be more interested in tech stuff than someone working in a beauty salon, I'm a bit confused as to how we should evaluate this, but I mean, the hit rate thing might be one way, and then yeah, not 100% sure. I mean, they just leave one out just to have a quicker evaluation, I guess. But I guess the thing I'm confused about is how does this user-based collaborative filtering and item work in this case, because we can just send it in, right? I mean, there's something that I'm missing. If I have RTX 3060 Ti and i7, can I do undervolting? Why wouldn't you be able to do undervolting? Yeah, I think here, I think this is probably when you would do this user and item based. I think it might be different for neural collaborative filtering because then you have the neural network that you can just input stuff to and you get the actual prediction. Because here you just get to, here you need to actually compute similarities, right? Yeah, I mean, you should not, for undervolting, you should not be scared, I think. Just, like, the worst thing that happens is that you give it too low voltage and it shuts down, and then you reset. So, like, it might freeze, for example, and then you restart your computer, and, like, if you don't have it, that it should save those by rebooting, right? If you don't have it that start at boot, that particular program, then it will just reset. Like, undervolting will not ruin your card. If you're open to being sidetracked, could you help me find bug in my RNN implementation? I might do that, but not right now. Is it like from scratch, or are you doing it RNN on something? Do you have research done in multi-criteria rexes? I don't know. I don't even know what that is exactly. I'm pretty new to recommender system, so. Are these live stream regular scheduled timetable? If I could just catch this, so I'd have traction. Not right now. I don't have a schedule. I'm just kind of doing it when I feel like it. It's from scratch, just character level RNN to generate Shakespeare. Yeah, I mean, I have done a video on that. I did that a long time ago. You could compare yours to mine because I did do the exact same thing. I don't know if you've checked it out. I think I did it for like name prediction or something, but it's the same thing. Like text generating LSTM. You could compare to this. It's just 140 lanes. All right, we need to get, let's see, we need to figure out how to do the next step. I guess we'll just continue reading here because maybe we'll get a better understanding on evaluation. Because that's kind of the thing is, reading can be quite difficult sometimes. So we could, maybe we could just find a nice YouTube video and watch a little bit. Sometimes it's good to just get ideas, you know? Recommender systems, evaluation. I mean, we can look at the machine learning specialization. I remember I took a look at it a little bit, but maybe you understand more the second time. I would like to do these kinds of projects, you know? We would, at the end of this. All right, I can do that. I can schedule the live stream, but like, I don't have a plan right now, so. But I could do that, yeah. Maybe if it's for like something more special, or I have something in mind, then that would be good. This is a
all right.
long
So
mess.
then let's actually get started on the counterfactual learning evaluations tutorial for recommender systems. My name is Thorsten Joachims. I'm faculty at Cornell University, and
hi everyone, I'm Yuta Saito. I'm a first-year PhD student at Cornell University working with Thorsten.
So what we're going to do over the next 3, well, let's just impute the other values, right? We know machine learning. So let's try and predict what the other outcomes would have been. So in particular, we'll impute the expected reward here. So we're marginalizing out the. So we can use that action. Expectation is doing the.
Oh, cool. Sure. And the results.
I had used pi e in some estimator here for variance control, but
actually working as intended. And we are still at the very early stage of understanding.
plus b equals 0.99 times the mean squared parameters. You notice that this algorithm is update x as x minus the partial derivative with respect to x of the cost function as a function of w and b as well as x, then this algorithm actually works. Here's what I mean. If we had 3 users and 2 collaboration between users to help of a user rate, all the ratings by Eve will be 0. It turns if you go to an online shopping website and are looking at a specific item, say maybe a specific book, the website may show you things like, here are some other books similar to this one. Or if you're browsing a specific movie, it may say, here are some other movies similar to this one. How do the websites do that? So that when you're looking at one item, it gives you other similar related items to consider. It turns out the collaborative filtering algorithm that we've been talking about gives you a nice way to find related items.
Yeah, good idea. We could look at collaborative filtering GitHub. I assume this is the evaluate the performance, top K recommendation. Yeah, this is a good idea. It's written in Keras, but we can probably implement it in PyTorch, right? Maybe that's a good idea for a video too. NCF kind of from scratch. It doesn't seem to... I mean, this is simple, right? It's kind of just doing... This is the general one, I think. This is the one we want to take a look at a little bit more. It's using multiprocessing. All right. Evaluate one rating. Yeah, so here it's doing the predictions and it's doing users and MP array of items. So it's running all of them. And this is exactly what I was thinking the prediction would do. So it's just different that for the user, like the thing I have a difficulty wrapping my mind around is the user-based collaborative filtering and the item-based collaborative filtering, because it seems like when you use SVD and you use matrix factorization, you have to then score the similarity by using something like cosine similarity, and then you can get the top recommendations. But when, in this case, right, because we have a neural network, it's still collaborative filtering, but we can just ask the neural network like a black box, hey, can you give me for this user and this movie? And then we get the actual prediction, right? So I guess I'm just confused if everything falls into user-based and an item-based, then how is it? What does this fall under, I guess, is the question. But it's definitely a lot simpler doing it this way. I mean, that's what they're doing here. They're just computing, asking the neural network directly, and then they do a map item score of items, and then they evaluate top ranked list with get. So they have the ranked list, and then they do this thing, and they just return 1 if it's in the ranked list, and otherwise return 0. I mean, that's pretty simple. And also this score right here. So that might be a good idea, something we can implement. It didn't, but let's see what Andrew says on the finding related items.
As part of the collaborative filtering we've discussed, you learn features xi for every item I, for every movie I or other type of item that you're recommending to users. Whereas earlier this week, I had used a hypothetical example of the features representing how much a movie is a romance movie versus an action movie. In practice, when you use this algorithm to learn the features xi automatically, looking at the individual features like x1, x2, x3, you find them to be quite hard to interpret. It's quite hard to look at learn features and say, oh, x1 is this an action movie, and x2 is this a foreign film, and so on. But nonetheless, these learned features collectively, x1 and x2, or x1, x2, x3, however many features n you have, collectively, these features do convey something about what that movie is like. And it turns out that given features xi of item I, if you want to find other items, say other movies, related to movie I, then what you can do is try to find the item k with features xk that is similar to xi. And in particular, given a feature vector xk, the way we determine whether or not it's similar to the feature xi is as follows, is the sum from L equals 1 through n with n features of xkl minus xil squared. This turns out to be the squared distance between xk and xi, and in math, this squared distance between these two vectors, xk and xi, is sometimes written as follows as well. And if you find not just the one movie with the smallest distance between xk and xi, but find, say, the 5 or 10 items with the most similar feature vectors, then you end up finding 5 or 10 related items to the item xi. So if you're building a website and want to help users find related products to a specific product they're looking at, this would be a nice way to do so. For recommend, if there's a new item in your catalog, say someone's just published a new movie and hardly anyone has rated that movie yet, how do you rank the new item if very few users have rated it before? Similarly, for new users that rated only a few items, how can we make sure we show them something reasonable? We did see in an earlier video how mean normalization can help with this, and it does help a lot. But perhaps there are even better ways to show users that rated very few items, things that are likely to interest them. This is called the code start problem, because when you have a new item that few users have rated, or when you have a new user that's rated very few items, the results of collaborative filtering for that item or for that user may not be very accurate. A second limitation of collaborative filtering is it doesn't give you a natural way to use side information or additional information about items or users. For example, for a given movie in your catalog, you might know what is the genre of the movie, who are the movie stars, what the express user is of a can give you ratings of multiple items is a very powerful set of algorithms, but also has some limitations. In the next video, let's go on to develop content-based filtering algorithms, which if a user comes to a website and they're browsing a specific, today's recommender systems will sometimes need to pick a handful of items to recommend from a catalog of thousands or millions or tens of millions or even more items. How do you do this efficiently computationally? Let's take a look. Here's a neural network we've been using to make predictions about how a user might rate an item. Today, a large movie streaming site may have thousands of movies, or a system that is trying to decide what ad to show may have a catalog of millions of ads to choose from, or a music streaming site may have tens of millions of songs to choose from, and large online shopping sites can have millions or even tens of millions of products to choose from. When a user shows up on your website, they have some feature XU, but if you need to take thousands or millions of items to feed through this neural network in order to compute the inner product to figure out which products you should recommend, then having to run neural network inference thousands or millions of times every time a user shows up on your website becomes computationally infeasible. Many large-scale recommender systems are implemented as two steps, which are called the retrieval and the ranking steps. The idea is, during the retrieval step, we'll generate a large list of plausible item candidates that tries to cover a lot of possible things you might recommend to the user. And it's okay during the retrieval step if you include a lot of items that the user is not likely to like. And then during the ranking step, we'll fine-tune and pick the best items to recommend to the user. So here's an example. During the retrieval step, we might do something like, for each of the last 10 movies that the user has watched, find the 10 most similar movies. So this means, for example, if a user has watched the movie I with vector VIM, you can find the movies Hey with vector VKM that is similar to that. And as you saw in the last video, finding the similar movies to a given movie can be pre-computed. So having pre-computed the most similar movies to a given movie, you can just plot the results using a lookup table. This would give you an initial set of maybe somewhat plausible movies to recommend to a user that just showed up on your website. Additionally, you might decide to add to it for whatever are the most viewed 3 genres of the user. Say there's a user that's watched a lot of romance movies and a lot of comedy movies and a lot of historical dramas. Then we would add to the list of plausible item candidates the top 10 movies in each of these 3 genres. And then maybe we would also add to this list the top 20 movies in the country of the user. So this retrieval step can be done very quickly, and you may end up with a list of 100 or maybe of hundreds of plausible movies to recommend to the user. And hopefully this list will recommend some good options, but it's also okay if it includes some options that the user won't like at all. The goal of the retrieval step is to ensure broad coverage, to have enough movies to at least have many good ones in there. Finally, we would then take all the items we retrieve during the retrieval step and combine them into a list, removing duplicates and removing items that the user has already watched or that the user has already purchased and that you may not want to recommend to them again. The second step of this is then the ranking step. During the ranking step, you would take the list retrieved during the retrieval step, so this may be just hundreds of possible movies, and rank them using the learned model. And what that means is you will feed the user feature vector and the movie feature vector into this neural network, and for each of the user movie pairs compute the predicted rating. And based on this, you now have, out of the, say, 100 plus movies, the ones that the user is most likely to give a high rating to. And then you can just display the rank list of items to the user, depending on what you think the user will give the highest rating to. One additional optimization is that if you have computed the...
I mean, this makes sense, right? So let's see, if we go back, like if we do this in production, it would not be feasible, right? If we're doing kind of we take one user and let's just predict what this user will rate every movie in our entire database, and assume we have like millions and millions of movies. It seems like a lot of unnecessary compute. So doing something like this where we instead of running assuming it's a large neural network, we do something like this. It makes it a lot more feasible. So we just run it on a couple of hundred based on this, right? And then we run the neural network on a lot less than millions and millions of movies.
The ones that the user is most likely to give a high rating to, EU, and between how many items performance, but the algorithm will end up being slower. To analyze or to optimize the trade-off between how many items to retrieve, do you retrieve 100 or 500 or 1,000 items? I would recommend carrying out offline experiments to see how much retrieving additional items results in more relevant recommendations. And in particular, that would argue systems that are just as our recommender systems. Even though recommender systems have been very profitable for some businesses, there have been some use cases that have left people and society at large worse off. however you use recommender systems, or for that matter, other learning algorithms, I hope you only do things that make society at large and people better off. Let's take a look at some of the recommender system and a lot to example on the profit for the company. And so if a certain most useful to that someone's higher profitable, and if the business is more profitable, it can then bid higher for ads. It can afford to pay more to get users. And because it can afford to bid higher for ads, an online advertising site will show its ads more often and drive more users to this good known business that recognizes, that allows our effective amplifying conspiracy theories or amplifying hate and toxicity turns out to be harmful to individuals and to society at large. One amelioration for this, partial and imperfect, is to try to filter out problematic content such as hate speech, fraud, scams, maybe certain types of violent content. But again, the definitions of what exactly we should filter out is surprisingly tricky to develop. More, I hope you think through not just the benefits you can create, but also the possible harm and
zero to one. Not gonna recommend this to the users anyway. And the third key problem is to evaluate the record. And basically, this is just to ask the people to this is high rate item that use. One key challenge here is that this utility matrix is often very sparse. That means most people have three approaches movies to the user and to the user. And in this case, we'll probably recommend this item to the user since it's also of authors, titles, actors, and directors. Specifically, it can be a binary vector where each entry represents one actor. And let's say that if an actor is in the movie, then the corresponding entry of the vector can be set to 1, and otherwise it will be set to 0. And in the case of text, if the item
You can also use conformal prediction method to further narrow out the prediction set. Conformal prediction. This one? The precursor of developed in the 1990s. All right. Okay, but we don't have to go into it in more detail, but yeah, I mean, it's good to know at least that that's a problem that we have to think about, because doing it this way is probably not going to scale that well.
Items are actually text, then we can use the set of important words in the document as the item profile. The one natural question is how to pick the important features, frequency of term I or feature I in document J. So these are basically how many times mentioned by combining. So here's the first step. And once we get the item profile, we can then compute the user profile.
Yeah, it's good to know about
combining the item profiles from the user history. So we can do this by simply using the weighted average of all the item profiles that the user has rated. Or we can use a slightly advanced approach to compute the weighted average of only the top rated items. And once we get both the item profiles and user profiles, we can finally do the predictions or recommendations. So here's the idea. Given the user profile X, which is a high dimensional vector, and the item profile I, which is also a high dimensional vector, we can then estimate that similarity by computing that cosine similarity. And
I'll upload the first Lightning video this week, but I don't want to upload all of them at the same time, just to keep some type of consistency. So I'll upload once a week, but for members, I mean, they're available right away as a I don't have that many like benefits of being a member, so that's just one of them. Otherwise, they would just be unlisted and then uploaded once a week.
The cosine similarity is just the inner product of X and I divided by the norm of X and the norm of I. And as you can see here, the larger this number is, the larger this cosine is, the smaller this angle will be. And that means this item and this user has larger similarity. And this is why we call this metric cosine similarity. And after we get the cosine similarity for all the items, we can just rank all the candidate items by their corresponding cosine similarity. And then we can recommend only the items with the largest cosine similarity to the users. And next, let's talk about the pros and cons of content-based approach. The first advantage of content-based approach is that there's no need to use the data on other users, so there's no sparsity problem. This is because in content-based approach, we only need the items of the same users to build the user profile. And the second advantage is that it's able to recommend to users with unique tastes. In the next part, we'll talk about easy. For example, we can just get too huge of content-based approach is that finding appropriate features is actually very difficult. And this is the case for images, movies, and music. You may think that in the previous example where we have movie recommender system, we say that we can use a genre or actor to build the item much of all items outside. Next, let's talk about the evaluation of recommender systems. Basically, how to evaluate whether the recommender system is performing well or poorly. And let's say that we have this rating matrix where each row represents one user and each column represents one movie. The rating is on a scale of 1 to 5. For example, this entry means that user 1 gives a rating of 3 to movie 2. And usually we will withhold part of the data as the test data set, and we pretend we don't know these ratings, and we'll use the other ratings as training set. So basically we will use
This is a little bit confusing, maybe. Here he takes half the users, he takes half the movies, but in reality, we want to take for every user, so we want to like gray out like one of these.
use the training set to predict the unknown ratings here, and we will evaluate how close the
But this is exactly what we did. So
prediction can be to the ground truth ratings. And we can also have another choice of splitting the training test set. For example, we can, for each user, we can select 20% of his or her ratings and put it into the test data set and put the remaining 80% into the training data set. And there are actually a lot of public data sets that we can use to evaluate the performance of recommender systems. For example, we can use
yeah, it should be uniformly distributed. I don't know, I think this gray thing is just confusing.
Test data.
Or what do you mean by uniformly distributed? In this case, it's still going to be uniform, right? We take, for every user, we take a random 20% of the ones that they've rated. So we would take away, 1/5 of these ratings for every user, depending on how many they've actually rated.
Set and put the remaining 80% into the training data
Oh, but
set.
maybe then it would, maybe that would be problematic if we have one user has rated 1,000 and another user has rated 5, right? I don't know how to solve that.
And there
In reality, it's nowhere near uniform distribution. Yeah. That would be a problem if that would be the case. I mean, in the neural collaborative paper that we looked at, they just took the like one rating for each user, the last one I think, and did that. Yeah, not sure.
Into the test
Let's see what he
data
says.
set
Maybe
and
he
put the
addresses this
remaining
issue.
80% into the training data set. And there are actually a lot of public data sets that we can use to evaluate the performance of recommender systems. For example, we can use data set that are called movie lens, and these are data set that contains a lot of ratings from quite a large number of users, and the ratings, they have different versions of movie lens ranging from 100K ratings to 10 million ratings. And we can also have another data set, which is the Netflix data set that has 100 million ratings. And all the historic user ratings constitute the ground truth. And to evaluate the performance of recommender systems quantitatively, we need to have some evaluation metrics, right, in order to measure the error rate. And one of the metrics is mean absolute error, or MAE, that basically computes the deviation between the predicted ratings and the actual ratings, as laid down by this equation here. We can see that we're actually using the absolute value here, and PI is the predicted ratings, RI is the actual ratings. And another matrix we can use is the root mean square error, which is normally called RMSE. And this is very similar to MAE, but it actually places more emphasis on larger deviation. You can see that it has a quadratic form. So basically, this error actually goes up pretty quickly as the deviation goes up. And this is why we say that it places more emphasis on larger deviation. Let's take a look at an example. Let's say that we have these columns as the ratings, and this column is the corresponding predicted ratings. Then to calculate which given this number, we care less to actually evaluate how accurately we can predict the ratings. But in practice, we actually couldn't care less about the actual ratings, especially the low rating items. This is because we usually want to predict only a ranked list of recommendations. Let's say that in the top-end recommendation setting, we usually provide a length and recommendation list for each user, and we'll examine the hit items, or we can say the correct items in the recommendation list. For example, in this recommendation list.
So if we go to this, or if we do a prediction here, define predict step, we get user movie rating from the batch. We run forward user movie, and then we get out. So this would be for, oh, this is for a particular batch. Let's say we send in the user ID. Oh, pass. We would do something like this. In their evaluate here, they ranked predict MP array of items. We would probably want to have save it. So we have self and like this, and then we could rank that. So we could sort it kind of, and then take the top 10 and then look with the hit rate.
The recommender system provides 5 items, and only 3 of them are correct items. So the target.
This is a little bit confusing though, because what do we mean by correct items? Correct items are the ones that they've rated, I guess. But they might still really like the first one here. It's just that it's not in their watched list.
It user actually only purchase or like 3 of the items. And in this case, we can then calculate the confusion matrix. Let's say that in this table here, we have the recommender system recommended 5 items, and it got 3 of the items right. And this target user actually, it actually purchased 7 items in total, but 4 of them is actually not covered by the recommender system. Now we can calculate the number of items that are recommended by the system, and they're actually right. And the number in this case is 3. And this corresponds to the 3 items here. We can also calculate the number of items that are recommended by the recommender system, but are actually wrong. And the number here is 2, which corresponds to the first item here and the 5th item here. And we call these the true positives, and we call this the false positive. And these 2 set of items combined together, they actually constitute the set of all recommended items. And similarly, we can also take a look at the number of items that are not recommended, but are actually right. And the number is 4 here. And this corresponds to the 4 items here. And these are the items that the users like, but they are not covered by the recommender system. And these 2 sets of items combined together, they actually constitute the set of all good items. And after computing this confusion matrix, we can actually get 2 evaluation metrics, and one of them is precision, which is all 30 bits as a result of this to gain a 1. And let's take a look at these 2 recommendation lists. Apparently, the second list is better. Why? This is because the second list actually ranked one of the correct items, which is 237, at the top of the list. And if we only look at the precision of recall, their numbers are actually the same. And this is why we need rank metrics, which actually extend recall and precision to take the positions of correct items in a rank list into account. So again, the relevant items are more useful when they appear earlier in the recommendation list, like here. And this is actually particularly important in recommender systems, as
I mean, here we have to also look at that they were actually good, because he might have rated that movie as, I mean, are we only looking at the movies that he rated 5 that we took from the test set? Because some might be 1s, maybe. He hated that movie, but it's still in the list.
lower ranked items may often be overlooked by the users. So what kind of rank metrics can we use? One of the most famous one is the NDCG, or
so this is the one that they used in the paper.
Normalized discounted cumulative gain. And to calculate this NDCG, we need to first calculate the DCG, which is discounted cumulative gain. And we can calculate it using the equation below. And here it's simply a sum of P terms. And the I here actually indexes the position. And we can see that and the P denotes the position up to which the relevance is accumulated.
Okay, so here, okay, so this one actually takes into consideration the relevance of recommendation. So if we have 1 to 5, it would be, I guess, the score of the recommendation, and then P denotes the position at which relevance is accumulated. But yeah, okay, so it would go through the first rank, and so this would increase, it would be lower, so we take we sort of have most importance of the rank 1 and then less and less, I guess, and then we look at the actual score that we got for that one. If we have a score, I guess, in this case, what would we do if, for example, if we don't have it? Would we skip it then, I guess? Because we don't know if the user actually liked it or not. We sort of don't have a value for it.
For example, the P in this.
What's the difference between these two? DCG CG discounted cumulative gain. It's the exact same, but it's 2 raised to and then minus 1.
Rank list we can set to 5, and will I, this one is actually, you can say that it's binary, or you can use auto scale. It actually returns the relevance.
Wonder if Torch Metric has this one. PyTorch Lightning ideal discounted cumulative gain. I mean, this is pretty simple to code, so, but just
Of
curious.
the recommendation at position 1. For example, in this recommended list, the relevance of the position 1 is actually 0. Therefore, the DCG, the first term of this DCG is actually 0 over log 2, which is also 0. And similarly, the second term of this DCG, since this is a correct item, therefore the numerator will be just 1. And the denominator, since it's in the second position, the denominator will be log.
That seems a little bit confusing to me. I don't know what you guys think, but if, for example, here we have 5 movies that we recommend to this user, and the user has not seen rank 1 or rank 5 that we recommend. So, we don't know, is this a good movie to recommend or not? But he has watched 2, 3, and 4, and so we do have a rating for those. To me, it makes sense that we would skip the ones that that the person has not watched, and only look at our sort of the ranks for those movies. I don't know, because it seems weird to punish the model or our evaluation here for recommending a movie that he has not already seen, right? I don't know. Let me know what you think.
I plus 1, which is log 3 here. And similarly, we can calculate all the other terms, and we sum them up, and this will be the DCG. And this is the first step. The second step is that we need to compute the ideal DCG. or the ideal discounted cumulative gain. And this ideal DCG is just the DCG when all the items are ordered by the ground truth decreasing relevance. So this would be the largest you can get if your recommended system is perfect. And once we have the DCG and ideal DCG, we can simply compute the NDCG.
Oh yeah, I didn't mean that it recommends that you've already seen. But I guess in a sense, yeah, because the evaluation metric is punished. I mean, so look, these movies here are from the test set, so it doesn't know that it's seen these movies. But when we're evaluating, we sort of take away 20% of the movies this user has seen and rated. So we have the actual ratings for these 20% that we take away and we put them in the test set. And then when we inference and we check, all right, what movies do we recommend to this user that we know sort of from the training data he has not watched. All right, these are the top 5. And then we look, all right, which ones are in this is my understanding at least, is that we look in the test set and we say, okay, 2, 3, and 4 are actually in the test set. So this is something that the user has, he actually did presumably like those movies. But 1 and 5 is not in the test set.
By dividing the DCG with the IDCG. For example, let's say that the number of total correct items is 3, then we can first calculate the DCG of this recommended list. And remember that we have only 3 non-zero terms. The first term is 0, therefore we ignore it. And the second term, the numerator is 1 because the relevance is positive. And since it's in the second position, the denominator is just log 1 plus 2, which is log 3. And in this case, the DCG for this recommendation list is 1.56. And then we will compute the ideal DCG, which is the ideal DCG of this recommended list. And this ideal list gives us a DCG of 2.13. Therefore, the NDCG is the DCG divided by the NDCG, which is 0.73. And another rank metric, which is also very famous, is the mean average precision. And it's a ranked precision metric that places emphasis on highly ranked correct predictions or correct hits. So essentially, this is just the average of precision values determined after each of these precision. We have one for the users.
All right, we got an overview there. Maybe we can look at this now. Yeah, thanks for joining, Clayton. See you next time. All right, so we have online and offline methods of evaluation. Online methods, let's see what they say. Offline methods are by far the most common method for evaluating recommender system from a research and practice perspective. So it will focus on offline methods. When working with offline methods, accuracy measures can often provide an incomplete picture of the true conversion. Several other secondary measures also play a role. Yeah, so I mean, evaluation is really important here, right? Evaluation goals. While it is tempting to use accuracy metrics for evaluating recommender systems, such an approach can often provide an incomplete picture. All right, so many secondary goals such as novelty, trust, coverage, and serendipity are important to the user experience. This is because these metrics have important short and long-term impacts on conversion rates. So I guess this discounted cumulative, what was it, gain, DCG, discounted cumulative gain, then that would be an accuracy type metric. Experimental design issues. All right, but I do hope that he goes through the accuracy metrics too, because user studies. Okay, online evaluation leverages user studies. Okay. Offline evaluation. What did they use? So RMSE, I guess. And SVD solution was the best. Would be cool to replicate this as well. All right, so here it goes into DCG. Man, there are a lot of metrics. And also ROC and precision curve. Well, I'm starting to feel a bit tired and also a little bit lost as to what to do. I mean, we want to have an evaluation metric. We do have one in the RM, just the mean squared error, but what's the next step in our approach? Should we use add an, what's the next step? Well, we definitely do want to add evaluation using probably DCG and DCG, and understand a little bit more detail of how they actually work. That seems to me to be the next step, and then probably use other models and compare results. Yeah, so we do matrix factorization and maybe other models as well. I'm not really sure what we do there, but it would be cool to sort of start with something really simple and then iterate, and then also introduce better and better models, and then see maybe in the end we can use some graph neural network and so on. That's probably the next step. We can do that now, but the metric we were using is probably not the best. Is this the same that they used here on the Neural Collaborative paper? This one? So NDCG at 10, they got 0.552. And here, movie lens 25. I mean, this is not better, is it? This seems worse, no? Or pretty much the same, maybe? So lower is better. I mean, here we got 0.54 and 0.5255. All right, so it's not that big of a difference, maybe. Or it's a different type of, because this is link prediction. Maybe it's not the same or comparable. Because this one here, NDCG at 100 though. Focal loss is a lot better, it seems. And I'm not sure why it used at 100 instead of at 10, but yeah. I'm just trying to get an idea of how important the model is, or sort of how much improvement we've made in the model department. But yeah, the next step is definitely, so what did we actually do in this one? Well, we converted to Lightning code, we added test train, and we learned a lot about different concepts, and we got an overview of how we actually do evaluation. Still a lot of things that are confusing. We need to understand this DCG better and then implement it.
The NDCG metric to evaluate recommenders, something that contains the position of that term. So I is the position in the order in which
my brain is too tired now. I have no idea. Like, what I'm confused about is basically for this one, we're only looking at the ones that we actually have in our test set. And I guess we have to do that. I mean, that makes sense because we don't have ratings for the other ones. But how are we incorporating our the ratings? So in this thing here, we are doing at k, so k ideal, we're summing up to k number of recommended ones. So we have recommender doc order. So we recommend document 10, document 3, document 1. We have relevance of 3, 4, and 5. And then we have the ground truth doc relevance. Okay, but so what if we have one predicted, but we don't have a ground truth? Do we skip it then? I mean, to me, it makes sense if we skip it. That's sort of my idea of how we should do it. Compute normalized discounted cumulative reward. Okay. Yeah. Okay, so for each so indices here are the order of which the prediction and target, and they should be equal here. So I think it makes sense that we can only compare the predictions with the ones that we actually have targets for. That makes sense to me. So here we would probably we would sort our predictions, and then we would do the same on the targets, and then send an indices 1 to n in sorted order. But we don't have to do that. It can also argument empty target action. Specify what to do with queries that do not have at least a positive. Okay. So, okay, it doesn't have to be a Boolean, first of all. Alright, so you can do multiple. If it's empty, you can do queries count as 0, and that's default. Consider only the top k elements for each query. Alright, so what this does for us is, I guess, compute both of them at the same time. Metric init retrieved. What's the class here, retrieval metric. All right, it runs retrieval normalized DCG, and this one check retrieval function. Okay, so it does a sorting here, and then it does the ideal target up to K. It computes the ideal DCG on the ideal target and the target DCG on the sorted target, and then I guess it just it divides the target DCG by the ideal. Yeah, and then DCG here is torch log 2. Yeah. All right, so it's pretty similar to what we saw, I guess, and we can run that. So we just need to do a prediction for a particular user, and then we send in targets. I'm not really sure what to do for this target, if we should skip or do negative or whatever. Are you thinking to provide Lightning tutorials for patrons? Yeah, I can. I mean, my idea was kind of to move from Patreon to just use YouTube, because I don't like to be active on multiple platforms and stuff. So, but if that's the case, then I'll see if I can integrate it in some way so that you automatically can become a member in some way. I don't know if YouTube allows that though. I'll think about it and see what I can do. But they should be available for both Patreons and YouTube members. But alright, I'll take a break now. We got an idea at least, and we'll see how to, I mean, what we'll do next is implement this IDCG, right? Or ND, what was it? DCG, ND, NDCG. The normalized discounted cumulative reward. So we'll do that using Lightning probably, but we want to understand how it works in more detail too, and then see some examples, maybe on the, you can compare to theirs, evaluate this get NDCG. So it gets the NDCG for a single one, and then it converts them, and I guess they do a mean maybe. but that's the next step. We'll figure that out next. And let's see else. We will also implement matrix factorization with SVD. And what are we gonna do in the book? I wonder if we're gonna do a lot more, because I want to get more practice and hands-on now and try to sort of build it and then evaluate it using different models. And I think that in that way we'll learn about this user-based collaborative filtering and item-based when we use the SVD approach, because I think that's how we do recommendations. All right, we'll see. We got an idea at least of where to start next, and I can maybe schedule that stream, because now it's 6 p.m. I'll be done for today, and then I'll continue on this, because I'll continue on this tomorrow, and I'll schedule the stream if you want to join. And remember, this is just kind of a chill stream, so like you can come by, you can ask questions, chat, and maybe help me figure things out if you want. And then later on, I'll do as I did for the Lightning series. So we'll do a more concise series on recommender systems, sort of introducing what they are, and we'll try to build it step by step, as with the Lightning series. But right now, obviously, I don't have the knowledge to make those videos. So the stream is for showing the messy process of learning stuff, and in that you can learn about it with me live. But don't worry, there will also be more concise videos in the future, hopefully. You know, when I learn about it, and then we'll, you know, as I usually make videos. So just for people that are thinking of like wanting to learn the material, it will come later as I usually make videos, and they won't be for members only. Everything I make will be uploaded later on to every sort of the Lightning series will also be uploaded. But yeah, that's the idea. And it would be cool to make this into a project that we can maybe deploy somehow. I would really like to build some type of, like, for this what would be cool here is to build a simple Flask website where you could, right now I'm being ambitious, okay, but this would be the idea, that we expand on this and we make a more state-of-the-art model, and we add a lot of more data, and then we make sort of an open source, I mean, obviously it's open source because I'm coding everything, right? But we make it, we make a simple Flask website where we have a data set of all movies, and then you can create a user, and you can sort of just rate all the movies you've seen, and then it will be sort of a personal recommender to you. And that would be open source and would be a nice project to showcase, and would sort of put everything together that we've learned about recommender systems. That's my idea, but we're not there yet. But tomorrow we'll continue, and we'll try to learn about this NDCG, and we will try to implement the matrix factorization. So let's make this clear. Tomorrow, understand and use NDCG, use SVD, SVD and compare results. And I think that's pretty much it. Yeah, that's it, like the main things that we want to do. I'll schedule the stream for tomorrow, guys, and we will continue from there. Yeah, I felt I wasn't that productive today. I feel like, I don't know. I mean, I did constantly try to learn stuff, right? But I don't know. This is just the way things are sometimes. Sometimes you don't get as far as you wanted to, but that's fine. As long as you put in the effort and sort of try to spend time learning it, it will, like, the brain has a magical power of like putting things together after a while, even though it can feel a lot really messy while you're doing it. And that's kind of how it is right now. There are so many different concepts and you're trying to like put them together. All right, do you guys have any questions before, or have anything before I close the stream? Thanks for joining, by the way. Boom. All right, guys, thanks for joining. And this is iTerm. It has, and I'm using PowerShell with iTerm 2 on Mac for the nice sort of the nice graphics of it, and then Tmux to attach to session, so that like if tomorrow, for example, when we continue, we're coding this, right? But and then I can just detach. If I shut down the computer and stuff, I can just do Tmux attach after SSH, and then we're back. Right, cool. All right, bye guys. I'll schedule the stream for tomorrow and you can join if you want. Bye bye.